meters per second. Okay, so that's kind of the basics of it for all the pieces of the wave. But what the heck is a wave? What is a wave? Let's take a look at that snake again, because that was the best example, weirdly enough, right? Okay, so my children are just gonna, I think this is the weirdest thing when they finally see it. Okay, but here we go. So there you go. I have a definite structure, right? I have this thing that's going like this along the length of this snake, right, until it gets to the other end. But does the snake move? Well, up and down it certainly does, doesn't it? And you might even say, because it's kind of like compressing like that, some parts of it must be kind of moving back and forth. You're right on those both points, okay? It is going up and down a little bit, and it is each point within the snake, right? If you look at these lines, they'll move something like this, okay? They will move back and forth. They'll go this way, but they'll also go this way. But in the end, where does everything end up? Pretty much where it started. And that's true for most waves. So what the heck is a wave? If everything starts out in one place and it ends basically in the same place, what is it that we're looking at? It's an interesting concept, okay? It's a propagation of a disturbance it's really the name of the thing, okay? That's the definition of the thing. And that sounds like something from Star Wars, right? There's a disturbance in the snake here, okay? But what is a wave really? It's a propagation of a disturbance, but it's really a transfer of energy. So what am I doing here? And I want you to see this, okay? Think about the tail end here, okay? I'm going to raise my hand up. So what happens in terms of potential energy? Well, with an increasing height, I get more potential energy, right? Decreasing height, I release it as kinetic. So I actually am changing my energy somehow as I go through here, okay? And what happens? This thing ends up where it began. So its energy starts out at 0, goes up and down, and then ends at 0. So I do have a change in energy, but it comes out as 0 here. So where does the energy go? Well, along here, along the wave, it actually travels along the wave. So what is the wave doing here? It's transferring energy. What is my voice doing right now? My vocal cords in here are vibrating like crazy, okay? But what are they really doing? They're actually moving, and this is kind of a freaky way of looking at it, right? End on, that tells you a lot of information. So I'm going to tell you about another kind of thing in a second here. But sound waves act differently. This is how they behave. They act like this, okay? They vibrate that air like this as it goes through. It's a pressure wave, okay? And in fact, nuclear blasts, when those things went off, the thing that actually destroyed most of the stuff around was actually a sound wave. It was this massive concussive blast, right, that actually knocked everything down. It was a really intense sound wave. So it transfers energy too. Just like that nuclear blast can flatten a city, that's sound. But still, I have to take energy from my lungs and push it out as I'm speaking to you. So I'm still transferring energy into that air, and it is vibrating to reach you. So it is still a transfer of energy. What about light? Well, think about this. People put solar panels on their house all the time. Why? Because they can take that light wave that's coming through and they can absorb it. And when they do, they transfer the energy from the sun into that panel, which then can go into their house and do work. Okay? So pretty much always, people also say they transfer information, which is true. Okay? Which is true. If I vibrate it this way versus this way, I get a different amount of information that comes through there. But most of what it's transferring is actually energy. The information is kind of a side effect. I mean, people will argue that, and physicists will even argue that. There is some more information, or more of a fundamental thing to information in some ways. But it's really transferring energy along. Okay, that's the job of a wave. But it just does so by propagating a disturbance of some kind. Really cool, though. And aside here, they've recently been able to measure gravitational waves for the first time about 5 years ago or something like that. So they set up 2 markers, okay, and they have like an L shape. So they have 2 sets of these things, so they can measure an X and a Y essentially, right? And what they did is they set up a laser with a timer on it, okay? So they can actually measure the length of time it takes for this laser to go from point A to point B. And these things are like kilometers apart. They're huge, just absolutely huge. And they're called LIGO because, they're in an L shape, right? It also, they turn the name into a fancy thing, but it's an L-shaped thing, okay? So it's a laser interferometry, whatever, a gravitational observation, that's what it is, right? Okay, so what they actually measure, though, is the distance, okay? The amount of time it takes light to go there. Light is at constant speed, so they can measure the time and then get the distance from it. Well, that means that they now have the distance between these 2 points. What a gravitational wave does, guys, is really cool. When you have 2 black holes way out in space, or 2 neutron stars or something extremely dense, and they actually run into each other and they merge, they create these ripples in space-time. What the heck does that mean? It actually means that the distance between any 2 particles actually changes. So when a gravitational wave from those things comes through, the distance between those objects actually shrinks and then grows and then shrinks and then grows. As do all of the atoms inside your body. They get closer and farther apart. Everything on Earth, everything in space between us and wherever those waves originated out, or some other black hole or something like that, they actually will change. They'll shrink and expand space itself, which is cool. But it's still a propagation of a disturbance, and it still carries energy, which is kind of cool. So that's the basics of our waves, okay? And I promised you one other thing. 2 kinds of waves. But for that, I'm going to use this red slinky. Off screen, you have no idea where this is anchored to. It's in space, right? It's the magical slinky, okay? So if you look at this, what can a slinky do? Well, it's already doing one thing, okay? So check this out. This is like a sound wave or a pressure wave or a compression wave, but it's called a longitudinal wave. Let me write that out, okay? So type of wave number 1, the kind that you don't really know that much about probably, or not that familiar with. That looks like a wave, right? This is different. So a longitudinal wave, longitudinal, like longitude, right? Longitudinal waves, and let me erase all this other stuff here first. Sorry, Slinky. All right. So let me get rid of this so you guys can actually see this, all right? A longitudinal wave is a sound wave or a compressive wave. So it is something that compresses and expands, like that gravitational wave I was just telling you about. So if you look at it, it's kind of hard to spot, but it looks kind of like, if you have a wave traveling here, it's compressed, and then there's a place where it's expanded. Then you have it compressed, and then expanded, and then you have a compression, and then an expansion and a compression. So it's a vibration like this. Let me show you what it looks like with a slinky, okay? So slinkies are great for this, as are springs in general. But if you look at this, let's see if I can get it to stop. Probably can't even get it to stop now. Okay, so if I get it started here, I'm going to pull this thing back, because that's how we start any kind of an oscillation, right? And we let it go, and look at this. Do you see how the slinky's going back and forth like that? That is your longitudinal wave. So what's the other kind of wave? Okay, the other kind of wave, the wave that you're most familiar with, that was longitudinal. The next kind is called a transverse wave. And let me also say this, okay? This is going to be basically our compression point, so that's going to be our peak, and this is going to be expansion point, so that's going to be your trough. So we'll call this a crest, and this is our trough, okay? And the direction the wave travels on a longitudinal wave, the wave travels in the same direction that the compression and expansion travels, okay? Transverse wave is very different. What is a transverse wave? It's the kind that you're most familiar with, okay? So what is a transverse wave? This is a transverse wave. Oop, until it snaps apart. I'll use the snake. Snake works better for it anyway. All right, so what's a transverse wave? This is a transverse wave. Don't you love physics with toys? So there you go. There's your transverse wave, okay? And look at this. The wave actually propagates from tail to head, okay? The wave actually propagates from the back towards the front. You guys can actually see it move along, right? So the wave goes this way. But which way does it vibrate? It vibrates up and down. Okay, so transverse wave is what you would think of as your typical wave, your ocean wave. That's a transverse wave. Why is it called a transverse wave? Well, the direction of motion is actually, that's the way the velocity is going, right? That's the velocity of the wave. It's going this direction. But which way is it vibrating? It's oscillating up and down, right? So this velocity is perpendicular or transverse, right? 90-degree angle in there. It's transverse to the direction of oscillation. So there you go. Your 2 types of waves, longitudinal, transverse. All of your components of a wave that you really need to know: wavelength, amplitude, speed or velocity, right? Frequency, how regularly it oscillates, or how many waves go past you in 1 second. And period, the amount of time it takes to get through one full wave to go past you. And that's really it, okay? So let me go ahead and stop this video now.